All right, looks like we're live, right? Let me see if I can hear myself. Hello, hello. Could you guys hear me? All right, there you go. Perfect. All right, so we're gonna start on chapter 2 of the book, and again, I'm gonna do all the work for you. All I got to do is follow along, and I do have the. Let me go to the flip a clip real quick. Uh, this is where I could write notes on here. Hold on. Oh, here it is. Oh, here are the notes from last time. All right, let's start a new one. All right, so notes number 99. Anyways, so again, I could write on here, so you guys could follow along. I do got my stylus right here, so I could write on the keyboard. Or I know you guys can't see shit, but anyways, I'm gonna do all the chemistry work. So this is gonna be chapter 2. I know normally that you guys can see that it's live. I know normally I've been procrastinating fucking doing this shit because fuck, dude. You guys read a chemistry book, but thank you guys for following along. If you guys are interested, yo, HCB, how's it been going? Oh, what's up, Atkins? What's up, G? Thank you for joining, man. Today I'm gonna do a little bit different. I'm actually doing chapter 2 of the chemistry book. If you guys want to learn chemistry, you guys could just tag along. Um, all my tanks are shut down right now. I do have the shrimp light to try to give me more light for the book, but anyways, yeah, this live is really about chemistry more than anything. But if you guys follow along, I will be doing all the chemistry work for you. So if you guys want to learn chemistry and you don't want to do the work, shit, just watch the video. Um, oh yeah, anyways, I've been procrastinating because it takes a long time just to do one chapter, and I'm not even in the math part. I'm just wondering how I'm gonna divide the book once I get to the chapters where it's gonna take a long time. My bad, the shutter on the camera. I forgot I have to every 5 minutes. All right, so Brenda, thank you for joining. Good morning, Brenda. Um, thank you for joining. And like I said, I am gonna do the chemistry book. So during this live, it's not gonna be any fish tanks, but yeah. Anyways, my saltwater tanks, Brenda, they've been doing so good actually. Um, I am gonna develop a new product hopefully, and all that shit. So I'm pretty happy. But my fish tanks are doing really good. Oh dang, the tanks are shut down. Oh my bad. Not shut down like that. I mean the lights are off. The tank lights are off. My bad. My light cycle, the tank lights are off. I did turn on the shrimp one. Shit. Let me show you real quick. Uh, my bad. I didn't mean it. I tore down the tanks, but I did. How do you Okay, there you go. I stopped the camera real quick. Hold on. Let me reposition. Anywho. Anyways, guys, yeah, the tank lights are off. That's the only reason. I didn't mean I shut them down. What the fuck? Okay, there you go. All right, bam. My bad. I had it. There you go. Well, it's focused right now. I'll try to focus page by page as I go. But anyways, I meant to say the lights are off. Okay. Laugh out good. Yeah, my bad, guys. No, especially the new SPS tank, the 14 gallon. Damn, that shit's growing good actually. I want to show you guys my SPS corals. Uh, I did a live earlier yesterday, but the tank lights were off also. I got a new water box 45 system, huge upgrade from the 10 gallon. Oh shit, that's what's up, bro. I'm gonna go check it out. After the live, I'll check it out. I've been so busy. Damn. Hey, but seriously, guys, thank you guys for joining. And like I said, I'm not gonna show any tanks today, but fuck, if you guys want to learn chemistry, shit, um, this is the video to be at. But remember, you guys talk amongst yourselves, and then once in a while, I will look at the comments in case you guys have any questions or whatever. Yeah. Anyways, let's. I'm just gonna start because fuck, it's gonna be a while. Anyways, let me put on my microphone, the headphones on real quick. There you go. All right, now I could hear myself. All right, so we're gonna start. So chapter 2. So here we go. Look around you. Notice the great variety of colors, textures, and other properties in materials that surround you. The colors in a garden scene, the texture of fabric in your clothes, the stability of sugar in a cup of coffee, the transparency of a window. The materials in our world exhibit striking and seemingly infinite variety. We can classify properties in different ways, but how do we understand and explain them? What makes diamonds transparent and hard, while table salt is brittle and dissolves in water? Why does paper burn? And why does oh shit, I lost. Why does water quench fires? The structure and behavior of atoms are key to understanding both physical and chemical properties of matter. Remarkably, the diversity of the properties we see around us result from only about 10 different elements, 100 different elements, and therefore about 100 chemically different kinds of atoms. In a sense, the atoms are like the 26 letters of the English alphabet and join in different combinations to form immense number of words in our language. But how do atoms combine with one another? What rules govern the ways in which atoms can combine? How do wait, how do the properties of a substance relate to the kinds of atoms it contains? Indeed, what is an atom like? And what makes the atoms in one element different from those of another? The chapter opening photograph is an image of a circle of 48 iron atoms arranged in a copper metal surface. The diameter of the circle is about 1/200,000th of the diameter of a human hair. Atoms are indeed very tiny entities. All right, so that's the shit it's talking about. Hold on, guys. Atkins, I'll check out your videos. Yeah. All right. So fuck, I still got 3 in the audience. Hey, thank you guys for joining. Like I said, I'm gonna do the chemistry book. You guys just follow along, and then once we actually start writing, I'll go to the flip a clip right here, and then I'll start writing. See that shit? I could just start writing. Only my stylus has been acting a little bit weird. All right. Anyways, back to the thing. All right, so let's go. So I'm up here in the top left corner of the book. All right, guys. It's hard for me to read from a distance and then try to talk into the microphone. Yeah, this is the best it's gonna get. Oh well. Hold on, let me see if I can bring the book towards me. No, I'm trying to focus as best as I can. Anyways, if you guys want me to focus on just one page at a time, let me know. But right now, I'm just covering the whole book. Anyways, the very striking image reveals the power of modern experimental methods to identify individual atoms, but it does not reveal the structures of the atoms themselves. Fortunately, we can use a variety of experimental techniques to provide the atom to gain a clever understanding of what it takes. Like in this chapter, we begin to explore the fascinating world of atoms we discover by what's it? Oh, whether we discover by such experiments. We will examine the basic structure of atoms and briefly discuss the formation of molecules and ions, therefore providing a a foundation for exploring chemistry more deeply in later chapters. All right, fuck. All right, 2.1. The atomic theory of matter. Philosophers from the earliest times have speculated about the nature of the fundamental stuff. Okay, so this is where it really people need to really pay attention. So this is really important on the chronological history of atoms and shit. This is really important, actually, guys. At least from the European standpoint. All right. All right. Philosophers from the earliest times have speculated about the nature of the fundamental stuff from which the world is made. Democritus, 460 to 370 BC, before Christ, and other Greek philosophers through wait, wait. Another early Greek philosophers thought that the material world must be made up of tiny individual particles that they called atoms, meaning indivisible or uncuttable. Later, Plato and Aristotle formulated the notation in which be no alt wait. Okay, there. And Aristotle formulated. Okay, let me read that shit. Indivisible, uncuttable. Later, Plato and Aristotle formulated the notion that there can be no uh ultimately wait, what the fuck? Ultimately indivisible particles. The atomic view of matter faded for many centuries, during which astro I don't know how to pronounce that. Aristotelian philosophy the dominated Western culture. The notion of atoms. Okay, so basically what it's saying is that the first Greek philosophers, they thought that atoms were made up of small stuff that can be cut up, and then eventually it was kind of lost in history. They didn't think too much about it. All right, the notion of atoms reemerged in Europe during the 17th century, which scientists tried to explain the properties of gases. Air is composed of wait, what the fuck? Hold on, guys. Let me grab something to read this shit with. It's because it's fucking hard to see from a fucking distance. Ah, fuck it. All right, there you go. The notion of atoms reemerged in Europe during the 17th century when scientists tried to explain the properties of gases. Air is composed of something invisible and in constant motion. We could feel the motion of the wind against us, for example. It is natural to think of tiny invisible particles as giving rise to these familiar effects. Isaac Newton, 1642 to 1727, the most famous scientist in his time, favored the idea of atoms, but thinking of atoms as invisible particles in air is very different from thinking of atoms as the fundamental builder blocks of elements. All right. All right. So what he's saying is that back then they couldn't explain gases, and Isaac Newton and everybody, they kind of speculated that atoms were real, but at the same time, it was beyond their imagination that atoms could exist in different forms. Like, for example, the gases in the air. Um, they thought of elements being more solids and liquids, but um, they didn't put together that gases, solids, liquids, and gases are all pretty much the same elements. Just in they all have different amounts of energy in them. All right. All right, anyway, so let's continue on. As chemists learned to measure the amounts of elements that reacted with one another to form new substances, the ground was laid. The ground was laid for an atomic theory that linked the idea of elements with the idea of atoms. The theory came from okay. The theory came from the work of an English school teacher, John Dalton, during the period from 1803 to 1807. Dalton's atomic theory involved the following postulates. All right, so this is the first guy that's really important in history. I mean, besides Isaac Newton, but for chemistry, this guy is really important in history. Actually, he's the one that put the ideas together. All right. Anyways, like I said, this is European history. This doesn't involve history of Raza and the way we did, or the way we learn about nature and stuff. Oh shit, damn! I got two people still on the live. That's some crazy shit. Anyways, thank you guys for still being here. Like I said, we're learning about the history of chemistry and all that shit, and I'm trying my best to record this with good audio and everything. All right, guys, and like I said, it's kind of like a way to teach people, and at the same time, it's notes for me in the future if I ever need to review shit. I could just rewatch my own video. But anyways, guys, I've been doing this shit for too long. These chapters seem kind of boring to me, but at the same time, I think it's really important for you guys to know how we got to where we are. Like the way I'm able to transmit this to you guys, and you guys are able to watch this. It all goes down back to these fundamental theories, and we should learn about this shit. I know at Raza we learn about other stuff, and usually we could be curious about subjects like this, but we were never really given an opportunity to learn. And I'm just happy you guys are still here watching and shit. But if you guys watch these videos, you guys are gonna learn more about chemistry, and nobody's gonna be able to fool you in anything. You should be able to know all this shit. Like, see, I already did this work previously. You see what I mean? Like, I already did the whole chapters. And I wrote some other shit. Anyways, let's continue on. So this guy, John Dalton, is really important. He lived from 1766 to 1844. That's not that long ago, guys. Anyways, let's continue. So he wrote some postulates. All right. So each element is composed of extremely small particles called atoms. All atoms are in a given element are identical to one another in masses and other properties, but atoms of one element are different from the atoms of all other elements. So basically, he's saying is that they're all similar, but they're different, and they all have their own unique properties. That's what he's saying. The atoms of one element cannot be changed into atoms of a different element by chemical reactions. Atoms are neither created or nor destroyed in chemical reactions. So what he's saying is that you can't destroy uh, a gold atom and form an oxygen atom. That's what he's saying. And then again, as we learned about atoms, we know by changing the amount of protons, you could change the element, but in order to do so, you're usually um, applying energy, and energy, like I said, you're just changing the energy, but you're not really changing shit. Um, but anyways, that's what he's saying is that you can't destroy or create atoms. That's what he's saying. Compounds are formed when atoms of more than one element combine. Given compounds always the same relative number of kind of atoms. Okay, hold on. Compounds are formed when atoms of more than one element combine. A given compound always has the same relative number of kinds of atoms. So what he's saying is that even if you combine 10 oxygen and 10 gold atoms, you still have 20 atoms. That's what he's saying. Um, and they're all relatively still similar. You know what I mean? It's still gold and it's still oxygen, just combined. Anyways, according to Dalton's theory, atoms are the smallest particles of an element that retain their chemical identity of the element. As noted in the postulate as Dalton's theory, an element is composed of only one kind of atom. A compound, in contrast, contains atoms of two or more elements. All right, there you go. So now it's starting to develop into atoms and molecules. Okay. Uh. Anyway, so I want to add. So what he's saying is that atoms are the smallest particles. It wasn't until we discovered quarks and shit like that that we found what protons and neutrons are made out of, and even they're trying to figure out if even something smaller than quarks. Okay, but atoms, what they're saying here is the smallest particle that contains something that's still something we know. If it's a gold atom, we know it's a gold atom. That's what he's saying. Okay. Anyways, moving on. Dalton theory explains several simple laws of chemical combination that were known during his time. One of these laws was the law of constant. Uh, what the fuck? Oh, so one of these was the law of constant composition. In a given compound, the relative number of kinds of atoms uh, damn it, are constant. The law is the basic of Dalton's postulate. For another fundamental chemical law was the law of conservation of mass, also known as the law of conservation of matter. The total mass of materials present after a chemical basis or postulate 3, Dalton proposed that atoms always retain their identities, and the atoms taking part in a chemical reaction rearranged in a given new chemical combinations. So right here they're saying is that they are speculating that atoms they hold their identity, but when they're combined with other chemicals, they change their arrangement and it forms a new chemical compound. They don't know how they are rearranged or any of that, but they're formulating and speculating that once they change, they form new bonds, like a new connection. Like I said, this is all in their heads. They still don't have any real um, experiments really to identify this. This is all just theory. You know what I mean? So when people think about the best way I could explain this is theoretical chemistry is the best way to explain it. It's everything that's in their heads. They're theorizing, or they're thinking this is the way the universe works. This is all theoretical shit. And fuck, they got a lot of it right. You know what I mean? So that's what they're saying. Brenda Love, I'll be listening while I go hit the gym. Oh shit, Brenda! Thank you so much, Brenda, for listening. That reminds me. After this, I'm gonna start. I'm actually gonna go to the gym after also, or just work out at home. But I gotta get my workout today. But thank you, Brenda, for listening. So, anyways, guys. So like I said, this is all the best way I'm able to explain it is theoretical chemistry was the foundation of how modern chemistry happened. Okay. And again, this is kind of happening around the same time during Newton's time. But anyways, let's read what this little caption says. John Dalton. Let's read a little bit more about him. So 1766 to 1844. That's about 150 years ago, which is not that long ago. All right. Anywhere from 200 to 200 was it 150 to 200 years ago, some shit like that. Dalton was the son of a Dalton was a son of a poor English weaver. He began teaching at the age of 12. He spent most of his years in Manchester, where he taught both grammar school and college. His lifelong interest in meteorology led him to the study gases, then chemistry, and eventually atomic theory. So, what the fuck is meteorology? That's basically it doesn't have to do with meters. Meteorology is basically studying the weather, like the gases, the clouds, and fucking the weather outside. You know what I mean? And from studying the weather outside, it um, it led into the study of gases, which basically studying gases. That's basically chemistry. And then from studying the chemistry of the air, he formed or started forming on the atomic matter theory. All right. So that was him. So he was the son of a poor English weaver. Anyways, so something you got to think about in 1776 or some shit. That's when the U.S. Signed a Declaration of Independence or some shit. So this is about 10 years before that shit happened. Okay, guys, when he was born. All right. So he was born before the American independence shit. Anyway, let's keep going. A good theory should explain the known facts and should be able to explain known facts and predict new ones. Dalton and his theory is deduced the law of multiple properties, law of multiple proportions. If two elements A and B combine to form more than one compound, the masses of B that can combine with the masses of A are in a given ratio of small whole numbers. We can illustrate the law of considering the substances water and hydrogen peroxide, both of which consist of element hydrogen and oxygen, forming water. 8 grams of oxygen combined with 1 gram of hydrogen in forming hydrogen peroxide. 16 grams of oxygen combined with 1 gram of hydrogen. In other words, the ratio of the masses of oxygen per gram of hydrogen in the two compounds is 2-to-1. Where the atomic theory, we can conclude that hydrogen peroxide contains twice as many atoms of oxygen per hydrogen atom as does water. So what the fuck did I just read? So basically, hydrogen peroxide, it's H2O2, and then water is H2O1. So there's only 1 gram of, there's one less oxygen atom in peroxide in water than there is in peroxide. So right here, they concluded that there's twice as many oxygen atoms in peroxide than there is in water. And that's why they got the ratio of 2-to-1. Okay, that's what the fuck I just read. I know it sounds fucking confusing, but yeah, fuck it. That's why I'm here to clear that shit up. All right, so give it some thought. One compound of carbon and oxygen contains 1.33 grams of oxygen per gram of carbon, whereas the second compound, 2.66 grams of oxygen per gram of carbon. What chemical law do these data illustrate? If the first compound has equal number of oxygen and carbon atoms, what can we conclude about the composition of the second compound? Basically, if there's more oxygen than the other one, then there's more of that shit. Anyways, fuck it. Let's keep going. All right, 2.2, discover the atomic structure. Dalton reached the conclusion about atoms based on one chemical observation in the microscope, in the microscopic world of the laboratory. Neither nor he nor those who followed him during the century after his work was published had direct evidence of the existence of atoms. Okay, let me stop that shit. So what he's saying is that during his time and even after they published the work, what is it? Even 100 years after they published his work, nobody has ever had direct evidence of the existence of atoms. This was just theoretical shit. Like I said, this is just what I call theoretical chemistry. Um, they're just they're speculating. They're just talking. That like, oh, this is the way we think it is, but we can't prove it yet. But this is the way we think shit happens. You know what I mean? All right, let's keep going. All right, well, let me reread that shit. All right, Dalton reached his conclusion about atoms based on chemical observations in the in the macroscope world in the of the laboratories macroscope. Oh, so what the fuck does that mean? It means the world of the big shit we could actually see. It's not a microscope, it's a macroscope. Basically, shit we could see. Neither he nor those who followed him during the century after his work was published had direct evidence of the existence of atoms. Today, however, we can use powerful instruments to measure the properties of individual atoms and even provide images of them. Figure 2.2. So here, I guess here's the image of atoms right here. So I guess now we could actually take pictures of atoms and shit. As scientists began to develop methods for more detailed probing of the nature of matter, the atom, which was supposed to be indivisible, began to show signs of more complex structure. We now know them. Well, we now know that atoms is the composed of still smaller subatomic particles. So basically, we know that atoms are made up of even smaller shit called quarks. Okay, guys. What are quarks made out of? We still don't know, but we do know that smaller than the atoms are quarks. Okay. Therefore, we summarize the current model of atom structure. We will briefly consider a few of the landmark discoveries. Discoveries that led to the model. We will see that the atom is composed in part of electrically charged particles, some which is positive plus charge and some with a negative charge. As we've discussed the development of our current model of atoms, keep in mind the simple statement of the behavior of charged particles. Particles with the same charge repel one another, whereas particles with unlike charges attract one another. Basically, two like charges repel, and then two different ones combine. So, anyways, another thing I wanted to add: the reason we have a positive, uh, or the reason why the electron is given a negative in science is because of Benjamin Franklin. He was the one that said that the electron is going to have a negative charge. Some people in physics wish that it was actually a positive charge, because when they do the calculations in physics, it would have made more sense for the electron to have a positive charge. But because of Ben Franklin and the way science was formulated, or the way they were what's it called, building this shit, they decided that the negative was gonna the negative charge was gonna be given to the electron. Okay, so that's why the electron has a negative charge because of Benjamin Franklin. Anyways, cathode rays and electrons. During the mid 1800s, scientists began to study electrical discharge through particularly wait oh during the mid 1800s, scientists began to study electrical discharge through particular evacuated tubes. Basically, the vacuum tubes is what we call it today. Tubes that had been pumped almost empty of air, such as those gases in figure 2.1 with a high voltage was applied to the electrodes in the tubes. Radiation was produced, thus, radiation called cathode rays originated from the negative electrodes or cathode. Although the rays themselves could not be seen, their movement was detected because of the rays cause certain materials, including glass, to fluoresce or to give off light. Scientists held conflicting views about the nature of the cathode rays. It was not initially clear whether the rays were invisible streams of particles or shit or new form of radiation. Experiments show that the cathode rays are deflected by electric or magnetic fields in a way consistent with there being a stream of negative electrical charge. The British scientist J. Thomson observed many properties of the cathode rays, including the fact that they are the fuck, I lost it. Oh, there you go. That they are the same regardless of the identity of the cathode material. In a paper published in 1897, Thomson summarized his observation by concluding that the cathode rays streams of negatively charged particles. Thomson's paper is generally accepted as the discovery of what later became known as the electron. So what they were looking at, they didn't know what the fuck they were looking at. They didn't know if it was a particle or if it was kind of some kind of light or some kind of radiation coming out of that shit. But then this guy uh realized he was dealing with something probably more unique, and eventually it was known that what they were observing were actual electrons. Okay. Thomson constructed a cathode ray tube having a fluorescent screen at one end, such as shown in figure 2.4, so that he could quantitatively measure the effects of the electric and magnetic fields on the thin stream of electrons passing through the hole and the positively charged electrode. These measurements made it possible to calculate the value of 1.76 times 10 to the 8 coulombs per gram for the ratio of electron electrical charge to its mass. That number is really important. So now they figured out a charge, or they got some kind of number, right? During the charge to mass ratio of the electron was known as measuring either the charge of the mass of electron would yield the value of the quantity. They go in 1909, Robert Millikan, some shit like that, 1868 to 1953, of the University of Chicago succeeded in measuring the charge of the electron by performing series of experiments described in figure 2.5. He then calculated the mass of the electron by using his experiment value for the charge, 1.602 times 10 to the negative 19 coulombs, and Thomson's charge mass ratio of 1.76 times 10 to the 8 coulombs per gram. Electron mass is equal to 1.602 times 10 to the negative 19. So that's the charge. And they divided it by the electron charge to mass ratio that Thomson had. And then they got the electron mass, which is 9.10 times 10 to the negative 28 grams. The result agrees well within the presently accepted values for the mass of the electron, 9.10938 times 10 to the negative 28 grams. The mass is about 2,000 times smaller than that of hydrogen, the lightest atom. All right. So fucking not even that long ago, guys. What was it? Like less than 100 years ago, or about 150 years ago. When was this? Between 1868 and 1953. So the earliest was like 50 years ago, or like 60, 70 years ago. They finally discovered the mass of the electron. So what we're saying is it's not that long ago, guys. Honestly, it was probably around like the early 1900s when they discovered this shit. But yeah, see, radioactivity. So we're gonna talk about radiation after. So, like I said, guys, the mass of the electron is really important in chemistry. But like I said, it wasn't that long ago when they discovered this. So less than 200 years ago. All right. Just to show you guys how far we've actually come. Oh shit! Hey, saludos, Benny from Benny de Cali. Hey, saludos, man. Rainer, what's up, G? What's Freedom GM? Oh, good morning. My bad. I'm fucking stupid. I'm thinking about a car. Anyways, Freedom Frog Gear. Hey, good morning. Thank you for joining, bro. Hey, I've been watching a lot. I'm definitely gonna get that Tika gun, bro. I'm thinking about that 308, bro. I'm like, oh shit, man. Interesting stuff. Shared it out. Thank you, Freedom. This is just really me teaching you guys chemistry. Normally, I don't do this, but we're gonna start doing a science series. That's why. Uh, Freedom. Good morning, Rainer. Thank you for joining, bro. Brenda, hi, Rainer. I said, guys, thank you guys for all joining. El Benny de Cali, saludos, and good morning to everyone. Thank you, bro, for joining, bro. I'm just showing everybody a little bit of chemistry. You guys just gotta watch and hear. Hopefully, I'll try to make it as interesting as I can. Good morning. Hello, Brenda Love. Good morning. Yeah, thank you guys for joining, man. I feel pleasure to have some kind of audience listening, guys. Thank you guys, honestly. All right, so back to the thing. All right, so less than 200 years ago, we finally figured out the mass of the electron. So the way that they got that was, remember, the charge. They figured out the charge. This man named JJ. Oh no, Robert Milkins, something like that. He discovered the charge and he divided by the electron charge mass from Thomson, and then he got the mass of the electron. Okay, and like I said, less than 200 years ago. Radioactivity. Okay, so here's another another really important discovery in physics and chemistry. After her discovery of radiation, physics hasn't really changed much. Chemistry and physics hasn't really changed much in the past 100 years. Okay, guys. So this is probably one of the last major contributions in science that we've seen. Oh, and besides the, genetics, but that's biology. That's not chemistry or physics. Genetics is the next major fucking accomplishment in science. But besides radiation, after that, chemistry and physics hasn't really fucking changed much, guys. Anyways, let's keep going. In 1896, I know, sorry guys, the shutter of the camera. I got to figure out how to bypass the shutter on the fucking camera. There was one video I was looking at, but I might try to do that. Anyway, so in 1896, the French scientist Henry Becquerel, something like that, 1852 to 1908, was studying a uranium compound when he discovered that it was spontaneously emits high energy radiation. This spontaneous emission of radiation is called radioactivity. Um, Becquerel's something like that Becquerel's suggestion, Marie Curie, something like that, and her husband Pierre began experiments to isolate the radioactive components of the compound. All right, so what the fuck did I just read? So it was a French scientist who really discovered radiation and the effects of radiation. And then it wasn't Marie Curie and her husband that really took those ideas and they really wanted to find out what the fuck they were looking at. All right, that's what I just read. Further study of the nature of radioactivity principles by the British scientist Ernest Rutherford, figure 2.7, revealed 3 types of radiation. This is why I fucking hate chemistry and physics. They fucking name everything the same. All right, anyways, there's 3 types of radiation: alpha, beta, and gamma. How fucking original, you faggots. Can't believe I just said that shit. Anyways, the radiation: alpha, beta, gamma radiation. Each type differs from its response to the electric field, as shown in figure 2.8. The paths of both alpha and beta radiation are bent in the electric fields, although the opposite direction. Gamma radiation is unaffected. So what the hell did I just read? One of them, I always forget which one. One of them's a helium particle. God, this is why I hate fucking the names that scientists give. Sometimes they're fucking retarded. Anyways, let's keep going and then we'll find out again. Roosevelt showed that both the beta rays consist of fast-moving particles, which were called alpha and beta particles. In fact, beta particles are high-speed electrons that can be considered the radioactive equivalent of cathode rays. They are attracted to a positive charge plate. The alpha particle has a positive charge and is attracted towards a negative plate. In units of the charge of the electron, beta particles have a charge of -1 and alpha particles have a charge of +2. Each alpha particle has a mass of about 7,400 times that of an electron. Gamma radiation is high energy radiation similar to X-rays. It does not consist of particles and carries no charge. We will discuss radiation in greater detail in chapter 21. All right. Man, hold on. Let me flip it real quick because I always forget the names also. God, anyway, we might just have to skip that shit. I'm trying to remember which one's which. So I know a helium particle. I think that's the beta. I don't know. Fuck you fuckers who named this shit. I would have just called it helium radiation or some shit like that. But fucking, they really fucked up the names. Honestly, I obviously don't agree with the names that people fucking give. It's like for fucking white people, everything's fucking gamma, fucking alpha and beta and all this bullshit, dude. It's like, dude, you guys are fucking retarded, man. Fucking name different shit. Stop calling different shit the same shit as some previous shit. Fuck you. Well, anyways, let's keep going. Nuclear atom. So we're at the nuclear phase, all right? So from studying radiation, what you want to take out of there is that they started to discover what atoms are made out of. So they started to discover that there's that one's a proton. I forgot which one's a proton. Well, obviously the proton's a positive one, but they started to discover the proton and the electron. All right, so that's what they're kind of going after this. All right, that's what's kind of happening here. Uh, anyway, so, but like I said, the reason they're not naming the compound right now is because it was all theory mostly. They never really understood what they're studying. You get what I'm saying? They didn't know what they were looking at. They were just measuring the effects of it. It's kind of like a magnetism. You don't know what the fuck it is, but you feel the effects and you're just studying the effects of it. That's what they're doing. The nuclear atom. With the growing evidence that the atom is composed of smaller particles, um, attention was given to how the particles fit together. During the early 1900s, Thomson reasoned that because electrons contribute only a very small fraction of the mass of the atom, they thereby were responsible for an equally small fraction of the atom size. He composed that the atoms consist of a uniform positive sphere of matter in which the electrons were embedded, as shown in figure uh, 2.9. The so-called plum pudding model, named after a traditional English dessert, was very short-lived. All right, so what the fuck did I just read? Before I read, we're gonna read what they were talking about. Milken's A oil drop experiment. Should I read those? Well, let's read them anyway. Yeah, let's read them. So let me start with the cathode ray tube experiment. Uh, Perpendicular magnetic and electric fields. The cathode ray electrons originate from the negative plate of the left and accelerated towards the positive plate on the right, which has given the whole center. They just skip that shit. So basically, what it's saying is that with the cathode rays, they find out that a magnet could change that could bend the light. And then over here with the oil drop experiment, with the oil experiment, they found the charge of the electron. Anyway, let's just keep going. Fuck all that shit. Ernest Rutherford. Rutherford, whom Einstein called the second Newton, was born and educated in New Zealand in 1895. He was the first overseas student ever to be awarded a position at the Cavendish Laboratory of Cambridge University in England, where he worked with J.J. Thomson. In 1898, he joined the faculty of McGill University, Montreal, which at McGill, Rutherford did his research on radioactivity and led to his being awarded the 1908 Nobel Peace Prize in Chemistry. In 1907, Rutherford moved back to England to be faculty member at Manchester University, where in 1910 he performed his famous alpha particle scattering experiments that led to the nuclear model of the atom in 1992. Oh, wait. Oh, sorry. No, my bad. That led to nuclear model of the atom. In 1992, his native New Zealand honored Rutherford by putting his likeness along with his Nobel Prize model and on their $100 currency note. All right. So even scientists get fucking noticed and shit. All right. So when M. Curie presented her doctoral thesis, it was described as the greatest single contribution of any doctoral thesis in the history of science, among other things. Curie discovered two new elements, polonium and radium. In 1903, Henry Buscuri, M. Curie, and her husband Pierre were awarded the Nobel Peace Prize in Physics in 1911. M. Curie won a second Nobel Prize, this time in chemistry. All right, so we're reading about that shit. Well, anyway, so we're talking about the first model of chemistry had to do with they knew that the electrons were were really small and contributed to the less to the size of the atoms. So they put the atoms outside, and imagine kind of like a snowball. The atoms, the electrons are on the outside, but they know that the inside is has a charged positive value, but they don't know exactly how they're arranged. But so that's why they called it the plum pudding kind of shit. But they didn't know, but that's how they started theorizing um, that the whole atom was actually solid, but the electron was outside. But it turned out to be wrong. But it it was the first model that they were trying to think of. All right. All right. Let's see. Brenda Love. Good morning from Albany. Finally got the roller fleece filter. Hey, Rainer, how does that shit? Is it cool, bro? I've been wanting to get one, but fuck, dude, I got nowhere to put one, so I don't have one yet. Good morning, guys. Driving. Thank you, Freedom Gear. Heading to work. Have a good one, y'all. All right. Thank you, Freedom. Freedom. Have a good day. Yeah. Thank you, guys. Honestly. All right, guys. So let's continue on. Fuck, man. I'm just looking at how much reading I have to do. And this is just reading. This is not even doing the actual calculations. Anyways, let's keep going. In 1910, Roosevelt and his co-workers performed an experiment that proved Thomson's model. Roosevelt was studying the angles in which alpha particles were detected or scattering as they passed through a thin gold foil only a few thousand atoms thick. Roosevelt and his co-workers discovered that almost all the alpha particles passed directly through the foil without deflection. A few particles were found to be deflected by approximately 1 degree, consistent with Thomson's plum pudding model. Just for the sake of uh, completeness, Roosevelt suggested that Ernest Marston, undergrad student working in the laboratory, look for evidence scattering at the large angles. Wait, what the fuck? Hold on, guys. I'm all reading retarded. Hold on. My knees are hurting. Hold on. Oh, shit. All right, there you go. Anyway, so let me reread that. A few particles were found to be deflected by approximately 1 degree, consistent with Thomson's plum pudding model. Just for the sake of completeness, Roosevelt suggested that the Ernest Martinson and undergrad student working in the laboratory look for evidence scattering. Scattering was observation in which they had come. Wait, what the fuck? To look for evidence scattering to large angles. To everyone's surprise, a small amount of scattering was observed at large angles. Some particles were even scattered back to their direction from which they had come. The explanation for these results was not immediate, obviously, but they were clearly inconsistent with Thomson's plum pudding model. Okay, so what the fuck did I just read? So basically, what it's saying is that if the plum pudding model was true, none of the particles should have gone through, but instead they're seeing that there's a lot of empty space in between the atom, and they couldn't figure out why, and that's what they're trying to discover why. All right. So subsequent experiment studies led to the discovery of both positive particles, protons, and neutron particles, neutrons in the nucleus. Protons were discovered in 1919 in Roosford. Oh, by Roosford. In 1932, British scientist James Chadwick, 1891 to 1972, discovered neutrons. We examine those particles more clearly in section 2.3. All right, so here's what I'm trying to get to you guys. In 1919, that's when they discovered the proton. And then what? 10 and like 12, like 13 years later, they discovered the neutron. And they discovered a neutron in 1932. So that was less than 100 years ago. So like about 90 years ago, they discovered the fucking uh neutron. So this is what I'm saying. Like a lot of new technology was based on discoveries that were made less than like 200 years ago, guys. It's something that's you guys should really understand. All this bullshit about aliens and all that bullshit. Sorry, guys. It's all bullshit. And like I said, guys, a lot of our discoveries of today's age is a lot of us are not giving credit for, or fucking some flat earth fucker fucking comes in and dismisses all our fucking efforts and shit to explain nature. But anyway, so in the gold foil experiment, the only thing you got to think of is that most of the particles pass through, and if that shit was solid, all of them should have bounced back, but only a few actually bounced back. So that's when they discovered that a lot of this shit had to be empty space. Kind of, if you look up here, they discovered it was empty space. That's what you want to take out from. Now you guys know why I don't do fucking these chapters fucking consistently, because goddamn, it takes a long time. All right, so we're in. Ah, fuck, dude, my legs are killing me though. I need something to sit on, guys. I need a chair. Hold up, guys. Let me go bring a chair real quick. All right, perfect. Fuck, man, that feels so much better. All right, the modern view and atomic structure. All right, since the time. All right, hold on. All right, there you go. Since the time of Roosevelt, physicists have learned much about the detailed composition of the atomic nuclei. In the course of these discoveries, the list of particles that make up the nuclei has given long and continuous. Hold on. Let me read that shit. The list of particles that make up the nuclei given along continues to increase as chemists, however, can take a very simple view of the atoms, because only 3 subatomic particles, the proton, neutron, and electrons, have a bearing on chemical behavior. All right, so what he's saying is that we found shit that's smaller than the neutron, protons, and electrons, but this is what makes up matter in the chemicals that we know of. Okay, the charge of an electron is negative 1.602 times 10 to the -19 coulombs, and that the proton is plus 1.602 times 10 to the negative 19 coulombs. The quantity 1.602 times 10 to the negative coulombs is called electronic charge. For convenience, the charge of atomic and subatomic particles are usually expressed as as multiples of the charge rather than its coulombs. Thus, the charge of an electron is -1, and that of a proton is +1. Neutrons are charged and therefore electrically neutral, which is how they receive their name. Every atom has an equal number of electrons and protons, so atoms have no net charge, no net electrical charge. Protons and neutrons reside together in the nucleus of the atom, which as Roosevelt proposed, is extremely small. The vast majority of the atom's volume is of the sphere in which the electrons reside. Wait, what the fuck? The vast majority of atoms' volume is the space in which the electrons reside. The vast majority of the atom's volume is the sphere in which the electrons reside. The electrons are attached to the protons in the nucleus by the electrostatic force that exists between particles of the opposite electrical charge. In later chapters, we will see that the strength of the attractive force between the electrons in the nuclei can be used to explain many of the differences between different elements. If an atom has 15 protons, how many electrons does it have? Where do the protons reside in the atom? So if it has 15 protons, more than likely it has 15 electrons, and the protons are resided in the nucleus. Atoms have extremely small masses. The masses of the heaviest known atom, for example, is approximately 4 times 10 to the negative 10 grams, because it would be cumbersome to express such small masses in grams. We use instead the atomic mass unit, AMU. 1 AMU equals 1.66054 times 10 to the 4 grams. The masses of the proton and the neutron, the masses of the proton and neutron are very nearly equal, and both are much greater than that of the electron. A proton has a mass of 1.07 AMU, atomic mass units, and a neutron has 1.087 atomic mass units. And an electron, 5.486 times 10 to the negative 4 atomic mass units, because it would take 1,836 electrons to equal the mass of one proton. The nucleus contains most of the mass of the atom. 2.1 summarizes the charge of the masses in the subatomic particles. We will have more to say about subatomic masses in section 2.4. Atoms are extremely small. Most atoms have diameters between 1 times 10 to the negative 10 meters and 5 times 10 to the negative 10 meters, or 100 to 500 pm. What the fuck is a pm again? Anyways, a convenient, although non-scientific unit of length used to express atomic dimensions are angstroms. I'm used to saying the angstroms for. Oh, PM is picometers. No, not picometers. Now that I fucking remember. Anyways, 1 angstrom, the diameter of an atomic nuclei are approximately 10 to the negative 4 angstroms. Only a small fraction of the diameter of an atom as a whole. Okay. We can appreciate the relative size of the atom and its nucleus by imagining as if the hydrogen atom were as large as a football stadium. The nucleus would be the size of a small marble, because the tiny nucleus carries most of the mass of the atom in such a small volume. it has an incredibly dense. It has an incredible density on the order of 10 to the minus 14 grams per centimeter cube. A matchbox a matchbox full of material in such density will weigh over 2.5 billion tons. Astrophysicists have suggested that the interior of a collapsed star are approximately or they may approach such this density. An illustration of the atom that incorporates the features we have just discussed and shown in figure 2.12. The electrons, which make up most of the volume of the atoms, play the major role in chemical reactions. The significance of the representation or representing the region containing the electron as a as an indistinct cloud, which hold on, an indistinct cloud uh, will become clear in later chapters when the consider the energies of spatial arrangements of the electrons. Atomic numbers. So what I just read is that the little electron cloud is basically the possibility where the electron may be. Anyways, the masses of the atom of one element differ from the atoms of another element. For example, how does one atom of carbon differ from an atom of oxygen? The significant difference in the subatomic composition of the atoms in such elements have a characteristic number of protons. Indeed, the number of protons in the nucleus of the atom of any particular element is called that element's atomic number. Because an atom has no net electrical charge, the number of electrons it contains equal the number of protons. All atoms of carbon, for example, have 6 protons and 6 electrons, where all atoms of oxygen have 8 protons and 8 electrons. Thus, carbon has atomic number of 6, whereas oxygen has atomic number of 8. The atomic number of each element is listed with the name of the symbol of the element in the inside front cover of the text. Atoms of a given number of differ in the number of neutrons they contain and consequently in mass. For example, most atoms of carbon have 6 neutrons, although some have more and some have less. The symbol 12C6 reads 12 carbon 12 represents the carbon atoms containing 6 protons and 6 neutrons. The atomic number is shown as a subscript, and which the superscript called the atomic, or it called the mass number, is the atomic mass of the proton neutrons in the atom. So what the fuck did I just read? Oh, so the number on top means how much the shit weighs, so how many protons and neutrons are together. And the atomic number in the bottom is the chemical symbol, which dictates how many protons are. And to figure out the amount of neutrons, you just take the whole mass number and subtract the protons, and you'll get the amount of neutrons. Because all the atoms of a given element have the same atomic number, the subscript is redundant and is often omitted. Thus, the symbol for carbon 12 can be represented simply as carbon 12. As shown, for example, the notation of atoms that contain the 6 protons and 8 neutrons have a mass number of 14 and are represented as carbon 14, 14C6, or carbon 14, and refers to it as carbon 14. Atoms with identical mass numbers and different mass numbers, thus is the same number of protons and different number of neutrons, are called isotopes. Are called isotopes of one another. Several isotopes of carbon are listed in table 2.2, and we will. So there's basically they're saying that there's different weights of carbon, and they call these isotopes. 2.4 atomic weights. Atoms are the smallest particle of matter, and they have masses in section In this section, we will discuss the mass scale of atoms and introduce the concept of atomic weights. In section 3.3, we will extend these concepts shown in how atomic masses are used to determine the masses of compounds and molecular weights. The atomic mass scale. Although scientists of the 19th century knew nothing about subatomic particles, they were aware that atoms of different elements have different masses. They found, for example, each 100 grams of water contains 11 grams of hydrogen and 89 grams of oxygen. Thus, water contains 88.9 and 11.1 ratio, 8 times as much oxygen by mass as hydrogen. Once scientists understood that water consists of 2 hydrogen atoms for each oxygen atom, they concluded that oxygen atoms must have 2 times 8, 16 times as much mass as hydrogen atom. Hydrogen, the lightest atom, was arbitrarily assigned a relative mass of 1, no units. Atomic masses and other elements were first determined relative to the value. Thus, oxygen was assigned atomic mass of 16. So basically, back then they didn't know anything about how much an atom weighs or anything, but using water, and they knew that water consists of hydrogen and oxygen through electrolysis. They saw that hydrogen, there was twice as much hydrogen and oxygen, and then if water consists of both of these, then that means water must be 16 times more heavier than the hydrogen, and they gave it atomic mass 16 or atomic unit 16. I believe oxygen in the periodic table is 8. Yeah, see, so the atomic number for oxygen is 8. So I mean, it has 8 protons, but if you look at the molecular weight, it's 16. So it has 16 neutrons. So that's what they were finding out on oxygen and shit. They were working their way up. They're trying to figure out elements, and they're trying to figure out how to weigh them out and calculate them, how to actually take measurements. You know what I mean? That's what they're trying to get. Today, we can determine the masses of individual atoms with a high degree of accuracy. For example, we know that the hydrogen atom has a mass of 1.6735 times 10 to the negative 28 grams, and that oxygen 16 oxygen 16 has a mass of 2.6560 times 10 to the negative 23 grams. As we noted in section 2.3, it is convenient to use atomic mass units AMU when dealing with these extremely small masses. 1 AMU equals 1.66054 times 10 to the negative 24 grams, and 1 gram equals 6.02214 times 10 to the 23 atomic mass units. The atomic mass unit is presently defined by assigning a mass of exactly 12 AMU to an atom of 12 carbon isotopes of carbon. In this unit, H1 atom has each hydrogen atom has a mass of 1.078 AMU, and oxygen has a mass of 15.9949 AMU. Basically, they're just trying to get weights of. They're trying to discover weights of atomic units and combine them with weights we could actually see. Average atomic masses. Most elements occur in nature as mixtures of isotopes. We can determine the average atomic mass of an element by using the mass of its various isotopes and the relative abundance. Naturally occurring carbon, for example, is composed of 98.93% carbon 12 and 1.07% carbon 13. The masses of these isotopes are 12 AMU exactly and 13.00335 AMU respectively. We calculate the average atomic mass of carbon from the fractional abundance of each isotope and the mass of that isotope. So they got carbon 12 and carbon 13. If you combine them, you get 12.1 AMU. So that's how they got the atomic mass units for that. Carbon 13 has 13 AMU. Anyways, that's how they got that shit. All right, so moving on. The average atomic masses of each element expressed in atomic mass units is known as atomic weight. Although the term atomic mass is more proper, average atomic mass is more proper, the term atomic weight is more common. The atomic weights of the elements are listed in both periodic table and the table of elements inside the front cover of this text. That's why you always see us with the periodic tables and shit. All right. A particular atom of chromium has a mass of 52.9 AMU, whereas the atomic weight of chromium is 51.9 AMU. Explain the difference of the two isotopes. All right, give it some thought. Calculating atomic weights of an atomic elements. Hey, should we do this shit? Let's try it. That way you can't say we didn't do an example. All right, naturally occurring chlorine is 75%. Oh, shit. All right, 75% chlorine, 35. The average atomic mass of chlorine and the masses of the isotope is closer to the value of chlorine 35. Oh wait, what the fuck? Wait. Naturally occurring chlorine is 75.78%, chlorine 35, which is atomic mass of 34.969 AMU. And 24% chlorine 37. So we got chlorine 35 and chlorine 37. And this has a atomic mass of 36.966 AMU. Calculate the average atomic mass, that is the atomic weight of chlorine. So in order to do this, you write the percentage. Fuck. I'm gonna write the percentage, which is 75%. You could write it as shit. Anyways, you get 75%. It's 7578. All right, so you convert the percentage to decimal point, and then you get the atomic mass unit was 34.969 plus you get the 24%. Times that by the other mass unit. Doing the calculator. There you go. So this is fucking chlorine. %75%. Chlorine 35. Fuck it. And this is chlorine 37. There you go. So you see that? So you have 75% chlorine, and this is the AMU. You multiply those two together, but you put this in a decimal form. Put this in a decimal form, and then you multiply both of those. See that? And you add them up. So this times that times that. When you add them up, it will give you that. All right. Now let's go check on the fucking chlorine. My bad, guys. Yeah, see, if you look at chlorine, it has 35.453 AMU. If you look at it, chlorine, it took the average amount of chlorine from the textbook. So if you look right here in the textbook, it's 35.453 chlorine atoms. I mean weight, and that's what we got on our fucking shit. At least we did a fucking example, I guess. All right, let's keep going. This fucking sucks. Damn, man, this fucking sucks. All right, let's keep going. Let's just read fast. The periodic table. Dalton's atomic theory set the stage for a vigorous growth of chemical experiments mentioned during the early 1800s. As the body of chemical observation grew, the list of known elements expanded. Attempts were made to find regular patterns in chemical behavior. These efforts accumulated in the development of the periodic table in 1869. We will have much to say about the periodic table in later chapters, but it is so important and useful that you should become acquainted with it now. You will quickly learn that the periodic table is the most significant tool that chemists use for organizing and remembering chemical facts. Many elements shown very strong similarities to one another. The elements lithium, sodium, and potassium are all soft, very reactive metals. For example, the elements helium, neon, and argon are very well non-radioactive gases. If the elements are arranged in order of increasing atomic number, their chemical and physical properties shown repeating or periodic pattern. For example, each soft radioactive metal, lithium, sodium, and potassium, comes immediately after one of the non-radioactive gases, helium. Neon gases and argon, shown in figure 2.15. The arrangement of elements in order of increasing atomic number, which elements having similar properties placed in vertical columns, is shown in the periodic table. The periodic table is shown in figure 2.16 and is known given on the front side of the text. For each element on the table, the atomic number of the atomic symbol are given. The atomic weight is often given as well as in the following typical entry for potassium. Atomic number 19, potassium symbol K, atomic weight 39.0983. You may You may notice slight variations in periodic tables from one book to another or between those of a lecture hall and the text. There are simply matters of style that they might concern a particular information, including there are no fundamental differences. Basically, it's saying all the periodic tables are the same shit, only some might have weights and shit like that. The horizontal rows are of the periodic table are called periods. The first period consists of only two elements, hydrogen and helium. The second and third periods began with lithium, sodium, respectively, consist of 8 columns each. The fourth and fifth periods consist 18 elements, and sixth periods has 32 elements. But for the two fit on page 14, and these elements with atomic numbers 57 and 7 appear in the bottom of the table. The what's it called? Oh, the seventh and the last period is complete, but also has 14 of its members placed in the row at the bottom of the table. So what he's saying is that on the table, these bottom elements right here, they actually go right there, but to fit on the page, they just put them down here. All right. Anyway, the vertical columns on the periodic table are called groups. Uh, the the way in each of the groups is labeled is somewhat arbitrarily. Three labeling schemes are in common use, two of which are shown in figure 2.16. The top set of the labels, which have A and B designation, are widely used in North America, Roman numerals rather than Arabic ones, are often employed in these schemes. Um, Group 7A, for example, is often labeled V11A. Europeans use a similar convention that numbers in the columns 1A and 8A, and from 1B to 8B, therefore giving the label 7B instead of 7A. The group headed in the flooring and the effort to eliminate confusion, the International Union of Pure and Applied Chemistry has proposed a convention that the numbers the applied chemistry or the numbers of the group from 1 through 1A is no with no A and B designations, as shown in the lower set of the labels in the top table of 2.16. We will use the traditional North American convention with Arabic numerals. Elements that belong in the same group often exhibit similar properties of physical and chemical properties. For example, the coinage metals, copper, Cu, Ag, and Au belong in group 1B, as their name suggests. The coinage materials used throughout the world to make coins. Many other groups in the periodic table also have names illustrated in 2.3. We will learn in the chapters 6 and 7 elements in the group of the periodic table have similar properties because of the same arrangement of electrons um, at their periphery of their atoms. However, we will not wait until then to make good use of the periodic table. After all, chemists who know nothing about electrons develop the table. We can use the table as intended to about electrons developed in the table. We can use the table as intended to correlate the behaviors of elements and the aid of remembering many facts. You'll find it very helpful to refer to periodic table frequently. When studying the remainder of this chapter, except for hydrogen, all the elements in the left side of the middle of the table are metallic elements or metals. The majority of the elements are metallic and share characteristic properties such as luster and high electrical and heat conductivity. All metals, with the exception of mercury, Hg, are solids at room temperature. The metals are separated from non-metallic elements or non-metals by by a diagonal step-like line that runs through boron to acetine, as shown in figure 2.17. Hydrogen, although in the left side of the periodic table is non-metal at room temperature, has some non-metal has some of the non-metal are gases, some are solids, and one in liquid. Non-metals generally differ from metals in appearance, section 2.17, and physical properties. Many of the elements lie along the line separates metals from non-metals, such as antimony, Sb, have properties that fall between those of metals and non-metals. These elements are often referred to as metalloids. So what the fuck did I just read? All right, so basically this little line right here, these elements are called metalloids because they have properties of both metals and non-metals. And then I forgot what I was saying. Anyways, that's all you gotta fucking know. Oh yeah, and then there's the alkaline metals, and just know that each one of these has a different name, and then going this way has a different fucking name and all that bullshit. Anyways, let's keep going because I just want to get this shit done. Glenn Seaborg, 1912 to 1999. The photograph shown at Seaborg in Berkeley in 1941 used a Geiger counter to try to detect radiation produced by plutonium. Geiger counters will be discussed in section 21.5. Prior to 1940, the periodic table ended at uranium element number 92. Since the time, no scientist had a greater effort on the periodic table than Glenn Seaborg. Seaborg figured 2.18 became faculty member in the chemistry department in the University of California, Berkeley in 1937. In 1940, he and his colleagues Edward McMillan, Arthur Wall, and Joseph Kennedy succeeded in isolating plutonium as a product of the reaction between uranium and neutrons. We will talk about reactions of this type called nuclear reactions in chapter 21. During this period in 1944 through 1958, Seaborg and his co-workers identified various products of nuclear radiations or nuclear reactions as being the elements having atomic numbers 95 found in nature. They can be synthesized only via nuclear reactions. For their efforts in identifying the elements beyond uranium, the transuranium, some shit elements. The Macmillan and Seaborg shared the 1951 Nobel Peace Prize in Chemistry. In 1961, 1970 to 1971, Seaborg and his served as a chairman at the U.S. Atomic Energy Commission's, now the Department of Energy. Atomic Energy Commissions. That sounds a lot better than Department of Energy. In the position that he had an important role in establishing international treaties and limit the testing of nuclear weapons. Upon the return to Berkeley, he was part of the team that in 1974 first identified the element number 106. Another team at Berkeley corroborated the discovery in 1993. In 1994, to honor Seaborg, many contributions, discovery of new elements, and the American Chemical Society proposed that element number 106, named Seaborgium, with a proposed symbol of Sg. Several years controversy with whether the element should be named of a living person. The IEPCU confidentially adopted the name Seaboranium in 1997. Seaborg became the first person to have an element named after him while he was still alive. That's some crazy shit. But this gentleman died in 1999. Fuck, I was 8 years old. So I was alive during the time when this guy was alive. Um, and 2 years before he died, that's when they named the element after him. So that was pretty cool. Molecules and molecular compounds. Even though the atom is the smallest representation of a sample of an element, only the noble gas elements are normally found in nature as isolated atoms. Most matter is composed of molecules or ions, both of which are formed from atoms. We examine molecules here in section 2.7. All right. A molecule is a assembly of two or more atoms tightly bound together. The result package of atoms behaves as many ways as a single uh, distinct object. As the cell phone, composed of many parts, can be recognized as a single object, we will discuss the forces that held atoms together, the chemical bonds in section 8 and 9, in chapters 8 and 9. Molecules and the chemical formulas. Many elements are found in nature in molecular form, that is, two or more of the same type of atoms are bounded together. For example, oxygen, normally found in air, consists of molecules that contain two oxygen atoms. We represent this molecular form of oxygen by the chemical formula O2. Red O2. The subscript of the formula tells the two oxygen atoms are present in each other in each molecule. A molecule that is made up of two atoms is called a diatomic molecule. Oxygen only exists in another molecular form known as ozone. Molecules Molecules of ozone consist of three oxygen atoms, making the chemical formula of this substance O3. Even though normal oxygen O2 and ozone O3 are both composed only of oxygen atoms, they exhibit extremely different chemical and physical properties. For example, O2 is essential for life, but O3 is toxic. O2 is odorless, whereas O3 is has a sharp, pungent smell. The elements that normally occur as diatomic molecules are hydrogen, oxygen, nitrogen, and the halogens. Their location on the periodic table are shown in figure 2.17. When we speak of the substance hydrogen, we mean H2, unless explicitly some shit indicate otherwise. Explicitly, whatever. Likewise, when we speak of oxygen, nitrogen, and any other halogens, we refer to as O2, N2, F2, Cl2, and Br2, or I2. Thus, the properties of oxygen and hydrogen listed in 2.13 are those of O2 and O2, O2 and H2. Other less common forms of element behave much differently. Compounds that are composed of molecules contain more or one types of atoms are called molecules. A molecule of water, for example, consists of two hydrogen atoms and one oxygen atom, and therefore represented by the chemical formula H2O. The lack of a substrate on oxygen indicates that one atom of oxygen per water molecule. Another compound composed of those same elements in different representative proportions is hydrogen peroxide, H2O2. The properties of hydrogen peroxide is very different from properties of water. Several common molecules are shown in figure 2.20. Notice that the composition of each element is given by the chemical formula. Notice also that these substances are composed only of non-metallic elements. Most molecular substances that will encounter contain many nonmetals. Most molecules and substances that we will encounter contain nonmetals. I think I missed something. Notice how the composition of each element is given by a chemical formula. Notice also that these substances are composed of non-metallic elements. Anyways, keep going. Molecular and empirical formulas. Chemical formulas indicate the actual number of types of atoms in a molecule are called molecular formulas. The formulas in figure 220 and molecular formulas, chemical formulas that are given in the relative number of atoms of each type in the molecule are called empirical formulas. The subscript in each empirical formula are always from the smallest possible whole number ratios. The molecular formula, the hydrogen peroxide, for example, whereas empirical formula HO, the molecular formula for ethylene is H2O H2H4, and its empirical formula is CH2. Hold on a sec. There you go. For many substances, the molecular formulas and the empirical formula are identical as in the case of water. Molecular formulas provide more information about the molecule than do empirical formulas. Whenever we know a molecular formula of a compound, we can determine the empirical formula. The converse is not true. However, if if we know the empirical formula of a substance, we cannot determine the molecular formula unless we have more information. So why do chemists bother with empirical formulas, as we see in chapter 3, contain more in chapter as we see in chapter 3, certainly common methods formulas is known. Additional experiments can be given information needed to convert empirical formulas to molecular one. In addition, there are substances such as most common forms of elements of carbon that do not exist in isolated molecules for those substances. We must rely on empirical formulas. Thus, all the common forms of element carbon is represented in an element's chemical symbol C, or the empirical formula for all the forms. Wait, what the fuck did I just read? I think I skipped a sentence. For those substances, we must rely on empirical formulas. Thus, all common forms of elemental carbon are represented by the chemical symbol C, which is the empirical formula of all the forms. Okay, now I get what it's saying. All right, so what's the difference between molecular formulas and empirical formulas? So, a molecular formula is basically the exact fucking shit it's made out of. Let's say um, hydrogen peroxide and water, they both have a different thing. So, hydrogen peroxide is H2O2 and water is H2NO. The empirical formula for both of them will just be an H for hydrogen and an O for oxygen. So, what the empirical formula is missing is the numbers, like the subscript number. Let me show you real quick. Bam. All right, so let me go to a different one. All right, so if you look at this, so these are molecular formulas right here. You see that the little 2, 2, 2, and the 1. Empirical formula would just have a hydrogen and oxygen. So how do we get empirical formulas? Let's say you put an unknown substance in a machine or in a computer, and then it tells you, oh, this thing is made out of hydrogen and oxygen. Okay, that's an empirical formula. Let's say the machine doesn't tell you the ratios. See the ratios right here? It doesn't give you that ratio number, but it will tell you that it's made out of this. And then it's up to us to figure out what the number is right here, the subscripts, these numbers right here. That's the difference between an empirical formula and a molecular formula. It's always better to have the molecular formula. An empirical formula is basically the shit that it's made out of. For example, a molecular formula for chocolate cake would be the chocolate, the sprinkles, 3 birthday candles, and this shit, right? The empirical formula would just say it's made out of chocolate, bread, and fucking candle wax. That's all. That's the best way I'm able to describe it. All right. Anyways, let's just keep going. Fuck it. Damn, we're at 2 hours almost. Picturing molecules. The molecular formula of a substance summarizes the composition of a substance that does not show how the atoms come together to form the molecule. The structural formula of a substance shows how the atoms are attached to within the molecule. For example, the structural formula of water, hydrogen peroxide, and methane can be written as follows. The atoms are represented in the chemical symbol and the lines used to represent the bonds that hold the atoms together. The structural formula usually does not depict the actual geometry of the molecule and its actual angles at which atoms are joined together. The structural formula can be written as perspective drawing. However, given some of these three-dimensional shapes as shown in figure 2.21, scientists can also rely on various models to help visualize molecules. Ball and stick models shown in atoms and spheres and bonds of sticks. These types of models has the advantage of accurately representing the angles at which the atoms are attached to one another within the molecule. In a ball and stick model, balls of the same size may represent all atoms, and the relative size of the balls may reflect the relative size of the atoms. Sometimes the symbols of the element are superimposed on the balls, and often the atoms are identical simply by color, or identified simply as color. The space filling model depicts of the atoms show which the fuck, dude. The space filling models depict the molecules would look like if the atoms were scaled up in size. The models show the relative size of the atoms, but the angles between atoms, which help define the molecular geometry. They are often more difficult to see than the ball and stick models, as in the ball and stick models that identifies the atoms and identified by the color, and they are also labeled by the elements by the symbol element. The structural formula of a substance, ethane, is shown here. Which of the molecular formulas be? Okay, let me write that shit. Ions and ionic compounds. The nucleus of an atom is interchanged by a chemical process, but some atoms can readily gain or lose electrons. If electrons are removed from or added to a neutral atom, the charged particle called an ion is formed. An ion is a positive charge, is called a cation. A negative charge ion is called an anion. To see how the anions form, consider the sodium atom, which has 11 protons and 11 electrons. The atom easily loses an electron. The resulting cation has 11 protons and 10 electrons. That means that it has a net charge of +1. The net charge of an ion is represented by the subscript. The subscript plus, 2 plus, and 3 plus, for instance, is a net charge resulting from the loss of 1, 2, or 3 electrons, respectively. The subscripts negative, -2, -3 represent the net charges representing from the gain of 1, 2, or 3 electrons, respectively. Chlorine with 17 protons and 17 electrons, for example, can gain an electron in chemical reactions by producing Cl- ion. We use a lot of the chlorine atom, the Cl- in salt water, so it's one fucking atom you should familiarize yourself with. In general, metal atoms tend to lose electrons to form cations, where nonmetals tend to gain electrons to form anions. That tends to be the common behavior pattern. All right. In addition to simple simple ions such as sodium plus and chlorine minus, there are polyatomic ions such as NH4, ammonium, and sulfate, SO4, sulfate ion. These later ions consist of atoms joined in as a molecule, but they have a net positive or negative charge. We will consider further examples of polyatomic ions in 2.8. This is important to realize that the chemical properties of ions are very different from the chemical properties of atoms, which shown in ions that are derived. It is important to realize that the chemical properties of ions are very different from the chemical properties of the atoms which the ions are derived. The difference is like the charge of a Dr. Jekyll to Dr. Hyde, although given atoms of its ion are essentially the same, plus or minus a few electrons. The behavior of the ion is very different from that of the ion atom. I think Dr. Jekyll and Hyde, that might be some kind of TV show or some shit. I don't know. Predicting ionic charges. Many atoms gain or lose electrons and end up in the same number of electrons as the noble gases closest to them in the periodic table. Members of the noble gases family are chemically very non-reactive, and form very few compounds. We might deduct this is because the electron arrangement is very stable. Nearby elements can obtain these same stable arrangements by losing or gaining electrons. For example, the loss of one electron of an atom sodium leaves it with the same number of electrons as the neutral neon atom, atomic number 10. Similarly, the chlorine can gain an electron, end up with 18, the same number of electrons as the argon, atomic number 18. We will discuss this simple observation to explain the formation of ions in chapter 8. We will discuss the chemical bonding, where we discuss chemical bonding. All right, good shit. So basically, all it's saying is that atoms and molecules gain or lose electrons to make them stable, to fit the arrangement on the atoms on the right side of the periodic table. They just want to get the orbitals filled or whatever. Basically, they want their outer shells to be filled or to be even, basically. All right. Damn, dude, how many more do I gotta go? Okay, we got like 10 more pages. The periodic table is very useful for remembering the charges of ions, especially for those elements on the left and the right sides of the table, as shown in figure 2.12 or 22. The charges of these ions relate to the simple way of their proposition. Of their positions in the table. On the left side of the table, for example, the groups 1A elements Uh, the alkaline metals form plus one ions, and the group two elements of the alkaline halogens. Oh wait, fuck, dude. For example, group 1A elements, uh, the alkaline earth metals plus one ions, and the group two elements, the alkaline earths form two plus, and the other side of the table, 7A elements with the halogens form one minus ions, and the group 6A elements form the two minus ions, as we will see in later chapter text. Many other groups of ions do not lend themselves to such simple rules. Okay, so basically it's saying that on this side, it's pretty easy to find out how many elements or how many electrons are given to what and what and what. Fuck, I'm just gonna skip that shit. I'm fucking tired, guys. Let's just keep reading. Ionic compounds. A great deal of chemical activity involves the transfer of electrons from one substance to another. As we saw, ions form when one or more electrons transfer from one neutral atom to another. Figure 2.23 shows when elemental sodium is allowed to react with elemental chlorine. The electron transfer from a neutral sodium atom to a neutral chlorine atom, we will left with the sodium plus ion and the chlorine minus ion. Because the objects of the opposite charge attract, Na plus and the Cl minus ions bind together to form a compound, sodium chloride. Basically, salt is what we use for the saltwater ocean and all that bullshit in our tanks. Sodium chloride, which is known better as common table salt, is an example of ionic compound, a compound that contains both positive and negative charged ions. We can often tell whether the compound is ionic, consisting of ions, or molecules, consisting of molecules, or molecular, which is the composition. In general, cations or metals are metal ions, whereas anions are nonmetals. Consequently, ionic compounds we can readily what the fuck? Compounds are generally combinations of metals and nonmetals, as in NaCl. In contrast, molecular compounds generally composed of nonmetals, H2O. The ions in ionic compounds are arranged in three-dimensional structures. The arrangement of Na plus Cl minus ions are NaCl is shown in figure 2.23 because there is no discrete molecule of NaCl. We are able to write only a empirical formula for the substance. In fact, only empirical formulas can be written for most ionic compounds. Hold on, guys. I'm trying to. All right, sorry. Yeah, I was trying to see what they were saying. Okay, good shit. Anyway, let's keep going. Figure 2.8 shows the elements essential for life. Fucking oxygen, all that bullshit. See, look. Additional 23 elements found in a variety of organisms. So calcium, chlorine, magnesium, potassium, sodium are fucking essential. And like I said, those are the ones we use in the salt water. Damn, guys, I gotta walk my dogs and I gotta finish this bullshit. It's already 7:21. Fuck, man. And I started this shit like around 5. Freedom, have a good day. Brenda, have a get ready for school. Yeah, Brenda, get that shit. See you next time. Thank you for teaching the Raza. I appreciate you, HCB. All right, Brenda, thank you. That was like almost an hour ago. I love you, Brenda. Thank you for joining, honestly. All right, let's go. Let's keep going, guys. I'm getting exhausted just reading this shit. All right, let's go. We can readily write the empirical formula as an ionic compound if we know the charges of the ions which the compound is composed of. Chemical compounds are always electrically neutral. Consequently, the ions and the ionic compounds always occur in such ratio that total positive charges equals the total negative charge. Thus, for one sodium plus ion and one chlorine atom negative, given NaCl, one Ba2 plus and 2Cl, given BaCl2, and so forth. As you consider these and the other examples, we will see that for the charges on the cation and anion are equal and the subscript to each other, to each ion will be given 1. If the charges are not equal, the charges on one ion without its sign will become the subscript and the other ion. For example, ionic compound formed by Mg forms Ng2 plus ions and N, which forms Na3 ions, Mg3 and Na or N2. All right, so basically it's saying you can figure out the ratios of shit based on the charges on the actual periodic table. All right. So if you look at a new name, so let's say you get Mg and then you get the nitrogen. So based on the charges on the periodic table, Mg has a plus, has a 2 plus, and the nitrogen has a -3. You see that shit? So the common number they have with each other, let's say it's 6, right? So if this is a 2 plus and you multiply it by 3, you get the 6, right? So you're going to get Mg 3, and then the nitrogen, it has a -3. If you multiply it by 2, you get the 6. So you get the 2 right here. So if you just avoid that fucking 6, right? If you see the charges right here on each one, the best way to go is just swap them out. Oh shit. Just swap them out. One goes here, and then the other one goes over here. You see that? So the charges of one, so you can see this has a -3 charge, and the magnesium has a +2 charge. And in order to figure out what goes here, the easiest way is just to swap them out. And then after you swap them out, figure out the charges. So 3 times 2 is 6. All right. So 2 nitrogen with the -3 charge will equal 6. 3 magnesiums with a +2 charge will equal 6. So that's how you know it. You can kind of check your answer. They both share charges of 6. You see that? I mean, it's either plus or -6. You see that? But the way I just figure it out when I'm calculating this shit, oh shit, is I always look at the charges, and then I just usually I just swap them out. But like I do what I do is I do calculate thing. You don't want to just fucking go based off rules. See that? They just fucking swap. That's all I did. That's what they're talking about. This was cool. Thank you, Brenda. Thank you for still being here. Honestly, I really love that. Thank you. All right. And like I said, I'm only going to be doing this science, like reading these chapters every so often because I am going to do the book, and that's a lot of fucking reading. Only next time I am going to break it up, though. I don't feel like doing all in ones. I'm only doing all in one videos just because it's just reading and no math. Once I start doing the math, then damn, that's going to suck. I'm going to really break it up. All right, give it some thought. Why don't we write the formula for the compound formed by calcium 2 plus and oxygen 2 minus as Ca 2 and O2. All right. And then it says calcium 2 plus and oxygen 2 minus. All right, so it's saying, all right, so right here it's saying, how come we don't write calcium 2 plus and oxygen 2 minus? How come we only write calcate or calcium and oxygen like that? And that's because if you look at over here, this has a -1 charge and calcium has a plus. Oh, wait, they gave us a 2 minus. So this one has a -2 charge and that has a calcium has a +1 charge. So it's a 1-in-1 ratio. And since you could divide this whole number by 2, you could just write calcium like that. You see that? And honestly, the charges are different. So calcium has a +2 charge. Oh, wait, oxygen does too also. Yeah, so it basically a neutral. It becomes neutral. Like the charges are neutral. Like for example, since they're both -2 charges, it's the same as 1-in-1 ratio. If these are 2 charges, then you would have calcium 4, oxygen 4. See what I mean? Anyways, fuck it. Let's just keep going. So with the charges, you're able to figure out what a molecule is made out of and all that bullshit, or the molecular formula. So let's keep going. Naming organic compounds. Fuck. To obtain information about a particular substance, you must know the chemical formula and name. The names and formulas of compounds are essential vocabulary in chemistry. The system used in naming substances is called chemical nomenclature. From the Latin word nomen, name, and clare, to call, there are now more than 19 million chemical substances. Naming them all would be hopelessly complicated task. If each had a specific name independent of all the others. Many important substances have known for a long time, such as water, ammonium, do not have individual traditional names, so-called common names. For most substances, however, we rely on the substance set of rules that are led to us to an informative and unique name for each substance based on the composition of its substance. What the fuck did I just said? So basically, certain things we name them and we group them together, like sulfates, sulfites, and shit like that. We kind of put them all in the same category. Instead of saying sodium chloride, we have all the chlorides together. We say a potassium chloride, sodium chloride, your mama's chloride. Like we just put them all together. If they, you know what I mean? It's easier that way. All right. The rules for chemical nomenclature are based on the division of substances into categories. The major divisions between organic and inorganic compounds. Organic compounds contain carbon, usually a combination with hydrogen, oxygen, nitrogen, and sulfur. All other inorganic compounds, early chemists associated organic compounds with plants and animals, and they associated inorganic compounds with non-living portions of our world. Although this distinction between living and non-living matter is no longer pertinent. Wait, pertinent. I don't know what the fuck. The classification between organic and inorganic compounds And section 2.9 will indicate the names of some simple organic compounds. Among or inorganic compounds, we will consider 3 categories of ionic compounds, molecular compounds, and acids. Okay. Basically, what I just said is that there's a whole bunch of different fucking names, and we try to put them all into a few categories. Names and formulas of iconic compounds. Recall in section 2.7, the ionic compounds usually consist of metal ions composed with non-metal ions. The metals from positive ions and non-metals from the negative ions. Let's examine naming the positive ions, then naming the negative ones. After that, we will consider how to put names of the ions together to identify the complete ionic compound. Positive ions, cations. Sodium, zinc, aluminum. Cations form when metal ions have the same name as the metal. Ions form a single atom are called non-atomic ions, monoatomic ions. There we go. If a metal can be different cations, the positive charge is indicated by a Roman numerical in parentheses followed by the name of the metal. So iron 2, iron 3 ion, copper 2, copper 1, shit like that. Ions of the same element have different charges, exhibit different properties such as different colors. Most of the metals can form more than one cation in transition metals, elements that occur in the middle block of the elements from group 3b and 2a, 3b to group 2b in the periodic table. The charges of these ions indicated by the Roman nomenclatures, the metals form one cation in the groups 1a, Na plus, Cl plus, K plus, and Rb plus. The group 2A, Mg2 plus, calcium 2 plus, strontium 2 plus, and barium 2 plus, as well as aluminum 3 plus, group 3A. The two transition metals, Ag, some shit, charges are not expressed explicitly by naming these ions. However, these are doubt in your mind. However, the metals form more than one cation. Use a Roman numeral to indicate the charge. If it's never wrong to do so, even though it is not unnecessary. What the fuck did I just read? All right. All right. So if we want to name shit, for example, we have iron 2 plus, then you have iron 3 plus. We could call it iron Roman numeral 2 ion, or we could say iron with 3 ion. You see that shit? That's all we're doing. That's all the fucking I just read, all that bullshit just to say that shit. The older method is still widely used to distinguish between two different charged ions in the metal to apply the ending ios or ic. For example, ferric or ferrous. All right. These ending represents the lower and higher charged ions, representing as they added to the root of the element Latin name. Ferrous ion, ferric ion. Copper, cuprous, and cupric ion. We will only rarely use these older names in the text. You might encounter them elsewhere. All right, so that's one thing important. The ferrics and the OUS and the ferric and all that bullshit. All it means is the amount of charges usually. Anyways, the names of formulas of the most common ions are shown in figure 2.4. They are also included in the table common ions in the back inside cover of the text. These ions listed in the left side of the table 2.4, the monatomic ions and that do not have various charges. Those listed in the right side are either polyatomic cations or cations with variable charges. The Hg2 2+ ion is unusual because this metal ion is non-metallic. It is called mercury 1 ion because it is because a non-atomic is not monatomic. It is called mercury 1 ion because it can be thought as two Hg plus ions bonded together. The cation that you will encounter most frequently are shown in boldface. You'll learn of these cations first. Oh, so what I just read is apparently mercury is like an exception kind of shit. Monatomic. Oh, okay, now I get it. So it's talking about the mercury. It's a Hg2 2+ ion because the mercury is not an atom by itself. For example, it has an H2, means that there's two mercury atoms bonded together that form the -2 charge. It's not mercury by itself forming a 2+ charge. That's what it was saying. Got it. How to reread that shit on myself. All right, negative cations, hydride, oxide, nitride. Yeah, we're gonna skip all that bullshit. All right, negative ions. The names of monatomic ions formed by replacing the ending of the name of the element with "ide," like hydride, oxide, nitride, shit like that. A few simple polyatomic ions that have the naming ending in "ide": hydroxide, cyanide, peroxide. Hydroxide is very important in the salt water, so you guys better know that shit. Polyatomic anions containing oxygen have naming ending in "ate" or "ite." These anions are called oxyanions. The ending in "ate" for the most common oxyanion in the element. The ending "ite" is used for the oxygen that has the same charge but oxygen atom fewer. But one oxygen atom fewer. So nitrate, NO3, and nitrite, NO2, sulfate, NO4, sulfite, NO3. Basically saying when one less oxygen, you could distinguish between the eights and the ites. Prefixes are used when the series of oxygen anions in the element expressed in four members of the halogens. The prefix "per" indicates one more oxygen than oxygen ending in "ate." The prefix "hypo" indicates one oxygen atom fewer than oxyanion ending in "ite." Perchlorate, one oxygen atom, then one more oxygen atom than chlorite. Chlorate. Perchlorate, one oxygen atom more than chlorite. Chlorate ion, Cl3. Chlorite, Cl2. One oxygen fewer atom than the chlorate. Hypochlorate ion, one oxygen atom lower than chlorate. Sorry guys, I'm out trying to read this shit real quick. Perchlorate, chlorate, chlorite, hyperchlorite. Fucking bullshit, dude. I'd rather just look at the molecular structure. All of them just had a one fucking oxygen atom less than the other. Anyways, moving on. Students have had a hard time remembering the numbers of oxygen atoms in the various oxyanions. The charges of these anions, figure 2.7, listed in oxyanions C, N, P, and carbon, nitrogen, phosphorus, and sulfur and chlorine that contain a maximum number of oxygen atoms. The periodic patterns seen in the formulas can help remember them. Notice that in carbon and nitrogen are the second periodic in the table, have only 3 oxygen atoms, whereas phosphorus, sulfur, and chlorine are in the third period and have 4 oxygen atoms each. If we begin with the lower right side of the figure CL, we can see that the charges increase from right to left, -1 for CL4, and 3 for PPO4, 3 minus, and the second period changes from right to right, from right to left, from -1 to -2 for all the fucking atoms. All right, fuck you. All right, we're moving on, guys. We're moving on quick, guys, because this shit got boring. Anions derive from adding H plus to the oxy anion, naming, adding as a prefix the word hydrogen, as dihydrogen, as appropriate. Carbonate ion, hydrogen carbonate, phosphate ion, dihydrogen phosphate. Ah, fuck, dude, I can't believe I'm reading this shit. Notice that each H plus reduces the negative charge of the parent anion and another number naming the anions and the properties. Wait. And the prefixes bi, thus HCO3 ion, commonly called bicarbonate, and HSO4, sometimes called bisulfate ion. The names of the formulas of the common anions are listed in the table 2.5 in the back inside cover of the text. Those anions whose names end in "ide" listed in the left portion of the table 2.5, and those whose names are in the eighth listed in the right. The most common for those on boldface show you learn the names of the formulas of these two anions, the formulas of the ions. Fuck, man. Removing the oxygen, notice the location, the thumb periodic table, in the group 7A, 1 plus some shit charges. Calcium chloride, aluminum nitrate, copper, some shit. Okay, guys, so the only thing I'm reading is it's important to know the charges of shit and all this shit to figure out the name of some shit. And even then, it's not really fucking perfect, because I could go and look at a fucking ingredients on something and I still don't know what the fuck they're talking about. The best thing to do is just fucking search that shit up, and then, yeah. But one thing is important is the sulfites, sulfates, chlorides, dichlorides, and all that bullshit. Oh, look, here's the chart. The only thing you really needed to know. Mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nana is 9, deca is fucking 10. From all the bullshit that I just fucking said, that's the only thing that's really important. And if you want to know the names of shit, like ides and eights and all that bullshit is also important. Names and formulas of acids. Acids is an important class of hydrogen-containing compounds, and they are named in the special way for our present purpose. The acid of a substance, those molecules yield hydrogen ions when dissolved in water. When we encounter the chemical formula of the acid, and the stage occurs. In the chorus, we will be written in the H plus. The H as the first element, and the Cl, and the H2 is SO4. The acid of a compound anion connected to the H plus ion neutral, balanced ion, the SO4 requires H2 plus ions, H2 name, and the acid name of the ion, some shit. Acids containing whose names in the ide and named by changing the ide ending into ic, adding the prefix hydro, the anion name for the following with the word acid in the following components: hydrochloric acid and sulfuric acid. Okay. I'm just gonna skip this shit. Acids containing whose ending in ate or ite, naming and changing the ate, ite to oos. The prefix is some shit. So perchloric acid, chlorate, chloric acid, chlorite, chlorous acid, hypochlorite, hypochlorous acid. Fuck, dude, this is some fucking bullshit. All right. Anyways, skipping on. I'm hoping I'm done, dude. What the fuck, man? I'm done with this fucking chapter. All right, good shit, guys. Good shit. We're almost there. Thanks for bearing with me. I'm almost crying. This is why chapters 1 and 2 fucking suck every year in the science classes, man. Names of formulas of binary molecule compounds. Procedures used in naming binary two-element molecular compounds are similar and those used in naming ionic compounds. The name of the element further from the left, the periodic table usually ran first. Exception of the rule occurs in the case of compounds containing oxygen. Oxygen is ran last except when combined with fluorine. I forgot about that shit. And both elements are in the same group of the periodic table, the one having the highest atomic number and the name first. The name of the second element given in the IED ending. Well, anyways, from all this bullshit, the only thing you gotta remember is that the positive fucking ion goes first and the negative ion goes second. That's the only fucking thing you gotta fucking take care of. Fuck this chapter. But yeah, positive ions first because chemists are positive people, and then the negative ions second. Fuck, dude. That's the only thing I fucking remember from the naming bullshit. Write the positive ion first and the negative second. The following example illustrates the rules: dichlorine monoxide, dinitrogen tetraoxide, nitrogen trifluoride, tetraphosphorus decasulfide. Fuck, and like I said, it is important to realize that you cannot predict the formulas of most molecular substances in the same way you could predict the formulas of ionic compounds. For the reason the name molecular compounds using prefixes that explicitly indicate their composition, molecular compounds that contain hydrogen and other one element, an important exception. However, these compounds can be treated as if they were neutral substances containing H plus ions and anions. Thus, you can predict that the substance named hydrogen chloride has a formula of HCl containing H plus to balance the charges with one Cl minus. The name hydrogen chloride is used only for the pure compound. Water solutions of HCl are called hydrochloric acid. Similar formulas with hydrogen sulfide, H2S, because two hydrogen plus are needed to balance the charges of the S2 minus. Ah, fuck, man. Fuck this shit. Fuck you. Fuck you. All right. Some simple organic compounds. The study of compounds of carbon called organic chemistry, as noted in the earlier chapter. Compounds are carbon, hydrogen, and some shit. We examined the some shit carbons in chapter 25. Relevant to chemical bond and biochemical systems. Here we present two brief introductions to some of the simple organic compounds. Hydrocarbons. Fuck. The alkanes, hydrocarbons. Compounds that contain one carbon and one hydrogen are called hydrocarbons. The basically use some shit of alkanes. There's methane, ethane, propane, all that bullshit. Some derived alkanes, other close organic compounds contain hydrogen atoms. Alkanes replace some shit groups. An alcohol example obtained by replacing hydrogen to the alkaline with an OH. You get methanol, ethanol, and propanol. So what it's saying is like when you get the acid kind of shit, you get the anes, like the methane, ethylene, propane, and when you get the hydroxides, you get the O's, like the methanol, ethanol, propanol, and shit like that. Alcohols have properties that are very different. You know what? Let me actually read that. That was actually pretty important. The study of compounds of carbon is called organic chemistry and are noted in earlier chapter. Compounds that contain carbon and hydrogen, often combination of oxygen, nitrogen, and other elements, are called organic compounds. We'll examine organic compounds and organic chemistry in detail in chapter 25. You will see the number of organic compounds throughout the text. Many of them have practical applications
or are relevant to the chemistry of biological systems. Here are present a very brief introduction to some of the simplest organic compounds, but provided you with a sense of what these molecules look like and how they are named. The alkanes. All right, so the alkanes. Compounds that contain only carbon and hydrogen are called hydrocarbons. In the most basic class of hydrocarbons, each carbon atom bonded to four other atoms. The compounds are called alkanes. The three simplest alkanes, which two, two, three carbon atoms respectively. The methane, CH4, ethane, C2H6, and propane, C3H8. The structural formula of these three alkanes are the following: methane, propane, ethane, propane. We can make longer alkanes by adding additional carbon atoms to the skeletal of the molecule. Although the hydrocarbons and binary molecule compounds, they are not named by the binary inorganic compounds discussed in 2.8. Instead, each alkane is the name of the ends in ane. The alkane with four carbon atoms is called butane. The alkanes and five or more carbon atoms named derived from the prefixes such as in table 2.6. The alkane and the eight carbon atoms, for example, are called octane, where octa prefixes with eight combined for and the ane combined with the alkanes. Gasoline primarily consists of octanes, that we discussed in chapter 25. Some derive some derived alkanes. Other classes of organic compounds obtained when hydrogen atoms of alkanes are replaced with functional groups, which specific groups of atoms. And alcohol, for example, is obtained by replacing hydrogen atom of an alkane with the OH group with a hydroxide. To me, that's to me the way I read it is one's an acid, is one's a base almost. The name of the alcohol derived from that alkane by adding the old ending: methanol, ethanol, and propane, propanol, propanol. Alcohol have properties that are very different from properties of the alkanes which alcohol are obtained. For example, methane, ethane, and propane are all colorless gases under natural conditions, whereas methanol, ethanol, and propanol are colorless liquids. We will discuss the reason for these different properties in chapter 11. The prefix 1 or I in the name 1 propanol indicates that the replacement of hydrogen with OH has occurred at the one of the outer carbon atoms rather than the middle of the carbon atom. The different compounds called 2-propanol, also known as isopropyl alcohol, is obtained by OH function groups attached to the middle carbon atoms. Oh, okay, now I get it. So it went from right here to there. Okay. The ball and stick models of these two molecules represented in figure 2.5. Much of the richness of organic chemistry is possible because organic compounds can form long chains of carbon-carbon bonds. The series of the alkanes begins in the methane, ethane, propane, and the series of alcohols that begin with methanol, ethanol, and propanol can both be extended for as long as we desire. In principle, the properties of the alkanes and the alcohol changes from the chains get longer. Octanes, which are alkanes and eight carbon atoms, are liquids under normal conditions. If the alkane series is extended to tens of thousands of carbon atoms, we obtain polyethylene, a solid substance that is make thousands of plastic products such as plastic bags, food containers, and laboratory equipment. Poly polyethylene, I believe that's fucking PVC pipe kind of shit. Writing structure. Anyways, we're fucking done, guys. That was the end of the chapter 2. I'm fucking tired, and go fuck yourself. That was a long fucking chapter of fucking reading bullshit. But yeah, guys, we're done. All right, guys, I'm just proud to announce we're we're on chapter 3 and we got to the good shit, guys. Fuck, dude. I'm fucking tired as fuck. Fuck this shit. Good morning, everybody. Oh, baby girl Wendy, thank you for joining. I'm actually done with chapter 2 of the chemistry book. It was a long ass chapter for me. The first 2 chapters are always fucking boring, but we finally got to chapter 3 when all the good shit starts happening in chemistry. All right. I believe that's when we actually start calculating shit. Oh yeah, see, there you go. We actually start calculating shit. So chapter 3 is the fucking beginning of the fun. Fuck. So in this chapter, we learn a little bit of the history and all that bullshit. And yeah, but thank you, baby girl Wendy, for joining. And everybody, Rainer, wow, you're still on. Yeah, bro, I'm fucking on, bro. I know, man. But anyways, guys, we're fucking done. Thank you guys for joining. Next time, we're just gonna actually look at the fish and shit. Fuck, man. I've been wanting to do chapter 2 for a while, like over a month now. But yeah, man, we're on chapter 3. We're on page 79. Fucking thank God. Fuck. All right, guys. I'll let you guys go and join me next time. And like I said, I might go live again talking about fish and shit. All right. But everything I do for fish and everything extends back to this fucking book. All right. And learning the basics of chemistry. And remember, guys, we're doing chemistry first and then we'll do physics second. All right. Fuck, man. We're out of here. Thank you guys for joining. And everybody that joined, seriously, thank you guys, honestly. All right. So I'll see you guys later.